Right. So this paper is about a new low latency technique, and it's written by me, of course, and then Seaman, Benedict, Joseph, and Ingrid as well. So I'll start with a short introduction regarding masking and low latency in general, and then I'll talk about some related work, and then I'll describe our masking technique, and then how we apply it to two S-boxes. One is Prince, and the other one is AES. And then finally, I'll show the implementation results that I have. So anyway, one popular way of masking is gate level masking, where you take an unprotected circuit and then you replace every gate with a masked version of it. So it's usually and an XOR, so we don't really have anything like OR or stuff. So an example for so XOR gates don't really introduce any latency to the circuit, but AND gates do. So for an example of an AND gate is a DOM in-depth AND gate. So it takes two inputs, X and Y, each share of two shares, and then it operates on one share each, X0, Y0, X0, Y1. And then some of those are refreshed, and then they're all stored in a register. So these registers are important for stopping glitches, and then, but it does introduce latency. Let's say I want to build a bigger circuit with a bunch of AND gates and a bunch of XOR gates, then I have to cascade a lot of them depending on what the algebraic degree of the function is. For example, for AES, it's at least 4 consecutive AND gates, which means you at least need 4 cycles of latency. And this makes low latency kind of hard to achieve, or it's usually a trade-off. If you go for low latency, then you usually have high area and randomness. So there are some previous work, which is, I think, all of these are first order secure. LMDPL and GHPC are definitely just first order secure. And yeah, so I'll start with LMDPL. So it was from 2014, and it's based on dual rail logic. So it's out of all these, and even comparing it to our work, it's the most efficient in terms of area and randomness. And then in 2018, there was GLM. So it's based on the DOM multiplier that I showed before. So you just skip the register stage. You don't compress anything. You just let it grow, and then yeah, it multiplies. After every nonlinear gate, it just keeps on growing. So that makes it very inefficient. So you have very high area as well as randomness usage. And then we have GHPC, which is also limited to first order security, and it is also not very efficient. It takes a very high area and randomness usage for especially for large functions. So I'll just explain our masking technique in a very simplified way. It's of course more complicated than this, but so the idea is to process shares in different cycles. So in the first cycle, I process one share of all the inputs, which is with the subscript 0, and then I do something with them, and then I mask them, and then I store them in registers. And then in the second cycle, I process the first shares, share one of all the inputs, and then I somehow securely combine them to produce the outputs. So I'll first explain with a simple example, which is a masked AND gate. So I have two inputs. So the first shares are X0 and Y0. So I multiply them like X0, Y0, and then I have X0 and Y0. So, and then I mask them with 3 random bits, R0, R1, and R2. And then those 2 columns are stored in 2 separate registers, the top 2 one. And then in the next cycle, I process the shares with subscript 1, and then I combine them with the whatever was calculated previously, which are stored in the registers, to get the outputs that I want. And also, I also refresh the inputs before I do any of this, which makes the gadget composable secure, which, as you can see, with R3 and R4. Yeah, it's a very small step, but it's kind of necessary. So, of course, that was a very small example, and it's not really efficient, and our technique doesn't really work well if we just do AND gates. So, but it becomes more efficient if we mask something larger, like a Prince S-Box or an AES S-Box. So, for a Prince S-Box, I have 4 inputs, which is A, B, C, D, and then 4 outputs, which are like 4 functions. It has a degree of 3 at most, and then yeah, you can see a lot of repeating terms. They all take the same inputs, A, B, and C, D. So the process is the same as the AND gate. So in the first cycle, I share 0 inputs of all the 4 inputs, A0, B0, C0, and D0, and then I compute all cross products except the degree 4 term. So it's like 14 terms, and then I need 14 random bits to mask them and then store them in registers. And then in the second cycle, I do the same with the shares with subscript 1, and then I combine them with the output from the previous stage, and then I get the outputs of the Prince S-Box and 2 shares each. So what are the advantages of this approach? First thing is that the value stored in the registers can be reused. So let's say if I look at one equation at a time, if I want to compute, let's say DC, then I use those 3 which are marked in red. And then if I want to now compute CB, then I use a different 3. And then for DCB, I use 7 of those registered values. And another advantage is that because all these 4 functions take the same inputs, I can also reuse all the registered values for all the different functions. I just have to compute it once and then add it to the equation that I need. So the main advantage efficiency-wise for our techniques comes from here. Now, so these are the implementation results for the S-Box alone. When I compare it with GHPC, its area is around half, and then the randomness is around 1/4 of it. And then now when I make a round-based Prince, so I have a bunch of linear elements, which is like shift row, mix column. I don't really have to worry about it. I just have to duplicate it for the 2 shares. But for the S-Box, I just create parallel instances of the masked S-Box that I showed before. Here's what it looks like. Here's what it looks like with the masked S-Box. So this has a latency of 1 cycle per round because I don't have any register stages outside the S-Box. And because it's also composable secure, we can do that. It's not a problem. And for the total prints, it's around 12 cycles. And here are the implementation results for the entire cipher. So it's much smaller than what exists before with 12 cycles as latency. And then the randomness is high, but I think it can be optimized, but we haven't really tried that, but yeah, it's an open problem. Next, the next application is AES S-Box, which is slightly larger than the Prince S-Box. It has 8 inputs and then 8 outputs, 8 functions as outputs. So I won't repeat what I said before. It's because it's the same procedure. So in the cycle 1, we process all share zeros, and then the cycle 2, we process all share ones, and then we somehow get the outputs as 2 shares of each function. So our S-Box has a latency of 1, which is true for any function. Doesn't really matter. So when I compare it with LMDPL, it's not as efficient. LMDPL is still more cheaper. It has less area and less randomness. But when I compare it with GHPC and GLM, it's 1/4 of the area, and then it also takes 1/8 of the randomness. It's like 260 bits instead of 2000 bits or something. Yeah. So conclusion. So we present a new technique, masking technique for low latency with a latency of 1, irrespective of what the function is. and then it doesn't really depend on the structure of the function or the representation of the function. I just need A and F equations, and then I can easily mask it. And it's also composable secure. That's a good thing. And then and then it also has less area and randomness than, at least less than GLM and GSPG, not less than LMTPL, of course. Yeah, thank you. Questions?